Imagine a visitor from beyond our solar system, carrying secrets billions of years old, racing through space at 210,000 kilometers per hour. Now imagine the James Webb Space Telescope just caught it doing something that shouldn't be possible. This isn't science fiction, this is happening right now, and what we've discovered is forcing us to rewrite the textbooks. In July 2025, our cosmic security system detected something extraordinary. The Atlas survey, that's our asteroid terrestrial impact last alert system, spotted a faint object moving in a way that immediately set off alarms. Its trajectory was wrong, its speed was impossible for anything from our solar system, and its path suggested it came from somewhere very, very far away. But here's where it gets strange. When we finally got the James Webb Space Telescope to lock onto this object, and believe me, that was like trying to photograph a speeding bullet from a moving car. We found something that made every scientist in the room stop and stare at their screens. The chemical signature was all wrong. Everything we thought we knew about comets, about how solar systems form, about the very building blocks of planets, it was being challenged by this single ancient visitor. This object, designated 3I Atlas, is only the third confirmed interstellar object we've ever detected entering our solar system. The first was Oumuamua in 2017, that strange cigar-shaped object that had everyone wondering if it was alien technology. The second was Borisov in 2019, which looked more like a regular comet. But this third visitor, it's rewriting the rules entirely. Let me put this in perspective for you. When we look at comets from our own solar system, objects like Halley's Comet that swing by every 76 years, we call them dirty snowballs. They're mostly water ice mixed with dust and rocks. When they get close to the sun, the water turns to vapor, creating those spectacular tails we see. It's been the same story for every comet we've studied for decades. Water is the main ingredient, always has been. But 3I/ATLAS. When Webb analysed its chemical fingerprint on August 6, 2025, the results were so unexpected that scientists initially thought there was an error in the data. This comet has 8 times more carbon dioxide than water. 8 times. In our solar system, it's completely the opposite. This discovery alone is forcing us to reconsider everything we thought we knew about how comets form. Think about what this means. This object formed around a completely different star, in conditions we've never seen before. It's been traveling through interstellar space for potentially billions of years. Yes, billions with a B, carrying with it a chemical time capsule from an alien solar system. And now, by pure cosmic chance, it's passing through our neighborhood, giving us a front row seat to study something we'd never be able to see otherwise. The speed alone tells us something remarkable about its journey. At 210,000 kilometers per hour, that's about 60 kilometers every single second. To put that in terms you can visualize, if this comet started at one end of a football field, it would reach the other end in less than 2/10,000ths of a second. This isn't just fast. It's so fast that our sun's gravity can't capture it. It's on what we call a hyperbolic trajectory, which means it's going to swing around our sun once and then shoot back out into deep space, never to return. This is our only chance to study it. There are no do-overs, no second opportunities. Once it's gone forever. Now, tracking something moving this fast with the James Webb Space Telescope was a monumental achievement in itself. Webb wasn't designed for this. It was built to look at distant, seemingly stationary objects like far-off galaxies. But our teams performed some of the most precise calculations of their careers. They had to predict exactly where this comet would be at the exact moment Webb was scheduled to observe it, accounting for its incredible speed, the telescope's own orbit around the sun, and even the tiny changes in the comet's path caused by gas jets shooting off its surface. The margin for error was essentially zero. One tiny miscalculation and Webb would be pointing at empty space, but they nailed it, and what Webb saw has left us all scrambling to understand. Using its near-infrared spectrograph, we call it NIRSPEC, Webb didn't just take pictures. It broke down the light from 3I/ATLAS into its component wavelengths, like a prism creating a rainbow. Each chemical element absorbs and emits light at very specific wavelengths, creating what we call spectral fingerprints. It's like each molecule has its own unique barcode, and the barcode we saw from 3I/Atlas was unlike anything in our databases. The carbon dioxide dominance is just the beginning of the mystery. This comet is telling us that wherever it formed, the conditions were fundamentally different from our own solar system's birth. In our neighborhood, comets formed in regions where water ice was plentiful, but 3I/ATLAS appears to have formed near what we call a carbon dioxide ice line, a distance from its parent star where carbon dioxide was the main substance cold enough to freeze. This single fact has profound implications. It means that the raw ingredients for making planets can vary dramatically from one star system to another. If comets in that system are rich in carbon dioxide rather than water, then any planets that formed there would have evolved completely differently. Their atmospheres would be different. Their potential for life as we know it would be different. Everything would be different. But wait, it gets even stranger. Despite all this gas shooting off its surface, and Webb observed massive amounts of it, the comet shows almost no non-gravitational acceleration. Let me explain why this is so bizarre. When a comet releases gas, it's like tiny rocket engines firing. These jets should push the comet slightly off its gravitational path. We see this with every active comet in our solar system, but 3I/ATLAS, it's moving along a path predicted almost perfectly by gravity alone, as if those jets don't exist. Scientists have proposed several explanations, and each one points to something extraordinary. Maybe the comet is so massive, current estimates suggest over 33 billion metric tons, that the gas jets simply can't budge it. That would make it one of the most massive comets ever studied. Or perhaps its internal structure is so strong and rigid that the jets can't form in the normal way. Or, and this is the really intriguing possibility, maybe the jets are coming out so evenly from all sides that they perfectly cancel each other out. Whatever the explanation, we're looking at something that doesn't follow the rules we've established from studying hundreds of comets over decades of observation. The age of this object adds another layer to the mystery. Based on its trajectory and speed, scientists calculate that 3I/Atlas could be between 3 and 11 billion years old. Our entire solar system is only 4.6 billion years old. This means we might be looking at an object that formed before our sun even existed, around one of the galaxy's earlier generations of stars. It's a fossil from the early days of our galaxy, carrying information about what the Milky Way was like billions of years ago. Think about the journey this object has taken. For billions of years, it's been sailing through the vast emptiness between stars. During that time, it's been bombarded by cosmic rays, high-energy particles that can penetrate deep into solid objects. It's been sandblasted by microscopic space dust. It's experienced the heat of passing near other stars and the deep cold of interstellar space. The fact that it survived all of this and still has enough volatile gases to create a visible coma is remarkable. Scientists believe that cosmic ray bombardment over billions of years created a dark, protective crust on the comet's surface, like a natural spacesuit protecting the pristine ices inside. Only now, as it approaches our sun, is that ancient seal being broken, releasing gases that have been locked away since before Earth existed. The global effort to study this object has been unprecedented. This isn't just NASA. This is a worldwide collaboration. The moment 3i Atlas was confirmed as interstellar, observatories around the planet reorganized their schedules. The Hubble Space Telescope provided crucial visible light observations, showing us the structure of the dust cloud. Ground-based telescopes in Chile and Hawaii maintained round-the-clock surveillance. The Neil Gehrels Swift Observatory used its ultraviolet instruments to detect the signature of water molecules breaking apart. Each telescope brought its own strengths to the investigation. It's like having a team of specialists examining a patient, one checking the heart, another the lungs, another running blood tests. Together, they're building a complete picture of this cosmic visitor. The Hubble observations revealed something particularly interesting, a distinct teardrop shape in the dust cloud surrounding the comet. This shape, caused by the pressure of sunlight pushing dust particles away from the sun, was unlike the patterns we typically see. The dust itself appears to have unusual optical properties, scattering light in ways that suggest the particles are either unusually small or have a complex, porous structure we've never encountered before. Even more intriguing, some observations detected traces of nickel in the comet's coma. Nickel is a metal that requires extremely high temperatures to vaporize. Finding it in the gas surrounding 3i Atlas suggests this comet either formed in a very hot region of its parent system or experienced some kind of violent heating event in its past. It's like finding evidence of both Arctic ice and desert sand in the same rock. It shouldn't be possible, yet here it is. This combination of cold chemistry, all that carbon dioxide ice, and hot chemistry, metallic nickel, is forcing us to think about planetary formation in entirely new ways. Maybe the disk of material that formed 3i Atlas' parent system was far more turbulent than ours, with hot material from near the star mixing violently with cold material from the outer regions. Or perhaps the comet formed in a cold region, but was later exposed to a blast of heat from a nearby exploding star. The implications extend far beyond just this one comet. If comets delivered water and organic molecules to young Earth, as many scientists believe, then the type of comet matters enormously. A young planet bombarded by water-rich comets like ours would develop very differently from one bombarded by carbon dioxide-rich comets like 3i/ATLAS. The chemistry of the atmosphere, the composition of any oceans, the potential for life, everything would be different. We're also learning about the incredible diversity of objects wandering through interstellar space. With 3 confirmed interstellar visitors now, we can start to see patterns. Oumuamua was bizarre and unexplained. Borisov looked familiar but had unusual chemistry. And now, 3i Atlas is showing us that there might be entire categories of comets we never imagined. Current estimates suggest there could be trillions of these interstellar objects passing through our galaxy at any given moment. Most are too small or too distant for us to detect, but occasionally, like with 3i Atlas, one passes close enough for us to study. Each one is a messenger from another star system, a free sample of alien geology delivered right to our doorstep. As I speak, 3i/ATLAS is heading toward its closest approach to the Sun, expected in late October 2025. Scientists predict dramatic changes as it heats up. New types of ice might start to vaporize. The coma could grow enormous. There's even a chance the nucleus could fragment, giving us a rare look at pristine material from its interior. But here's the frustrating part. During the most critical phase of its journey, when it's closest to the Sun and most active, 3i Atlas will pass behind the Sun from Earth's perspective. For several weeks, it will be lost in the Sun's glare, invisible to our most powerful telescopes. It's like the climax of a movie happening off-screen. When the comet emerges on the other side, it might look completely different. Did it survive intact? Did it break apart? We'll be waiting anxiously to find out. This is why the current observations from Webb are so crucial. There are before picture, documenting the comet's state in exquisite detail before it faces the full fury of our sun. Every measurement, every chemical signature, every piece of data is being carefully recorded. This information will be the benchmark against which any changes are measured. The teams are getting creative about observing during the blackout period. Spacecraft like the Solar Orbiter and Parker Solar Probe, which orbit the Sun at different angles, might catch glimpses when Earth-based telescopes can't. Radio telescopes might detect signals even through the Sun's interference. Every available tool is being deployed to maintain some connection to this precious visitor. What we're witnessing with 3i Atlas is more than just the passage of a comet. It's a fundamental shift in our understanding of the cosmos. For all of human history, we've been limited to studying our own solar system's comets, like trying to understand all of biology by only looking at one type of tree. Now, these interstellar visitors are showing us the full forest, the incredible diversity of planetary systems throughout our galaxy. This discovery is also a testament to human ingenuity and cooperation. The successful tracking of such a fast-moving object by Webb, the coordinated global observation campaign, the rapid sharing of data between nations. It shows what we can achieve when we work together toward a common goal. In an era of division, science remains a unifying force, bringing together people from every corner of Earth to decode messages from the stars. For me, personally, moments like these remind me why I fell in love with physics in the first place. Here we are, on a small planet orbiting an ordinary star, and yet we've built instruments capable of analyzing the chemical composition of a visitor from another star system. We can look at this ancient traveler and read its history like a book, understanding events that happened billions of years ago in a place we'll never visit. The data from 3i Atlas is still being analyzed. Scientists worldwide are poring over every detail, looking for additional clues about its origin and nature. Each new discovery adds another piece to the puzzle. The water vapor confirms it's not completely alien. It shares some chemistry with our comets. The carbon dioxide tells us its home was different. The nickel hints at violent events in its past. The unusual dust properties suggest new types of materials. Together, these clues are painting a picture of a solar system unlike anything we've imagined. This is also changing how we think about the search for life. We've always focused on finding Earth-like planets with liquid water, assuming that life everywhere would need the same conditions that life on Earth requires. But if other solar systems are built from fundamentally different chemical blueprints, perhaps life could arise in ways we haven't considered. 3i Atlas is reminding us to keep an open mind about what's possible in the universe. As this remarkable object continues its journey through our solar system, every observation is precious. We're racing against time, gathering as much data as possible before this cosmic visitor disappears back into the darkness. The pressure is immense, but so is the excitement. Every day brings new discoveries, new questions, new mysteries to solve. The strange chemistry, the impossible motion, the ancient age, the survival against all odds, each aspect of 3i Atlas challenges our assumptions and expands our horizons. It's showing us that the universe is far more varied, far more interesting, and far more mysterious than we ever imagined. This visitor won't be here long. In a few months, it will swing around our sun and head back out into interstellar space, continuing a journey that will last billions more years. It might pass through other solar systems, might be observed by other civilizations, might carry its secrets to places we can't even imagine. But for this brief moment in cosmic time, it's here with us, teaching us, challenging us, inspiring us. The story of 3i Atlas is far from over. As it approaches the sun, as we gather more data, as scientists work to understand what we're seeing, new chapters are being written. Each discovery leads to new questions. Each answer reveals new mysteries. This is science at its most exciting, not the memorization of facts from textbooks, but the active discovery of new truths about our universe. What makes this even more remarkable is that 3i Atlas is probably just the beginning. As our detection systems improve, as telescopes like Webb push the boundaries of what we can observe, we'll likely find more interstellar visitors. Each one will bring its own secrets, its own challenges to our understanding. We're entering a new era of astronomy, where we can directly study samples from other star systems without leaving home. The carbon dioxide discovery alone would have been enough to make headlines. But combined with everything else, the mass, the strange motion, the age, the nickel, the unusual dust, 3i Atlas is proving to be one of the most important astronomical discoveries of our time. It's not just adding to our knowledge, it's forcing us to reconsider what we thought we knew. For young scientists watching this unfold, this is your Apollo moment. This is the kind of discovery that inspires careers, that launches 1,000 research papers, that opens entirely new fields of study. The questions raised by 3i/ATLAS will take decades to fully answer. Some of you watching might be the ones to solve these mysteries. As we wait for the next phase of 3i Atlas journey, as it heads toward its solar encounter, the anticipation in the scientific community is palpable. Will it survive the intense heat? Will new types of ice begin to vaporize? Will we see chemical signatures we've never detected before? Every possibility is being modeled. Every scenario is being prepared for. This is also a reminder of how much we still don't know. For all our technological achievements, for all our scientific understanding, the universe continues to surprise us. A single comet from another star system has upended decades of assumptions. It makes you wonder what other surprises are out there, waiting to be discovered. The fact that we can even detect and study objects like 3i Atlas is a triumph of human curiosity and ingenuity. Think about the chain of achievements that made this possible. We built a network of telescopes to watch for asteroids. We developed the technology to track incredibly fast-moving objects. We placed the most powerful infrared telescope ever built at a special point in space. We created instruments that can decode chemical signatures from light itself. And we coordinated all of this in real time to study a visitor that we'll never see again. In the grand story of the universe, 3i/ATLAS is just a tiny footnote, a small comet from an unknown star briefly passing through our neighborhood. But for us, for humanity, it's a revelation. It's showing us that we're part of a much larger, more complex, more interesting cosmos than we ever imagined. Every star system might be unique. Every comet might carry surprises. Every observation might change what we know. As Brian Cox, I've spent my career trying to convey the wonder of the universe to people. But moments like these, when the universe reveals something completely unexpected, these are the moments that remind me why this matters. We're not just collecting facts about space. We're discovering our place in the cosmos. We're learning that the story of how planets and stars and comets form is far richer and more varied than any of us imagined. The journey of 3i Atlas from a distant star to our solar system, carrying its cargo of ancient ices and cosmic secrets, is a journey that connects us to the wider galaxy. It reminds us that our solar system isn't isolated. We're part of a vast, interconnected cosmos where objects can travel between stars, carrying messages from one system to another.